show you how to use PyTorch for maximum likelihood estimation. So let's say that this is our data, so the sample, so we read it in. So the shape of it is 200. So we have 200 data points. And let's say that the ones represent heads when we flip the coin and zeros represent tails, okay? And what we might like to know is, well, what's the probability of this coin coming up heads, right? So essentially, what's the probability of one here and one here and so on, okay? So if you took statistics, you know how to do it. So in order to compute P of heads, where heads corresponds to 1, you'll just compute the mean of the sample, right? So that's going to be 0.72. So great. But let's say that you don't know that and you instead want to actually do maximum likelihood. So how would you go about that? Well, first you need to figure out how to write the likelihood, right? So P of xi equals 1, so P of this or anything else being equal to 1, that will define as P, the probability of heads. That means that the probability of xi equals 0 is 1 minus P. The probability of heads plus the probability of tails is also going to be 1, so 1 is going to be P, 1 minus P. We can also write it as the likelihood. So the likelihood of xi being equal to 1 given P, right? So the likelihood of xi equals 1 for any of the xi's here. So this is x1, x2, x3, and so on. That's going to be P. That's going to be 1 minus P. We can use a trick to write this down as an algebraic expression. So what we'll do is we'll say, okay, so if P is equal to 1, then this expression should be xi, and it will be because P times 1 times xi is 1, but 0 times anything is 0, so what you are left with is P in case xi is equal to 1. On the other hand, if xi is equal to 0, then this part cancels out because it's 0, and this part is 1 minus P. So this expression is going to be 1 if xi is 1 and 0, P if xi is 1 and 1 minus P if xi is 0, exactly what we needed. So the likelihood is going to be the product of those terms for all the xi's, right? So the probability of x given P, so the likelihood of x, is going to be the product over all the i's of P xi given P, which is this guy. Now, usually we don't want to deal with products because this is going to be extremely small because all the likelihood is smaller than 1, right? So what we'll do is we'll take the log. So the log of a product of this product is going to be the sum of the logs. That's just how logs work. And finally, we take the minus because we want to work with the negative log likelihood. So that's the expression that we end up with. This is the expression that we want to minimize if we want to find the P such that the likelihood is as high as possible, because this is the minus log likelihood. So you could also maximize the actual log likelihood. So let's start working with Torch. So first we'll read in the sample into the variable x. So we need to convert it into a tensor and then into a Torch variable. And we also convert it to float. So in Torch, you must multiply types that are alike, right? So if you want to multiply two numbers, they have both to be floats, or both they have to be doubles, or both have to be ends, or something like that. And P is going to be a float, so we'll make x a float, and you do it using dot type like this. We'll also define P, so that's going to be a variable, and initially it's going to be random, right? So it's going to be, in this instance, 0.244, but every time you run it, it's going to be different. And here we say requires grad, so that means that we should be able to compute the gradient of any function of P with respect to P, which is something that we'll want to do because the negative log likelihood is going to be a function of P, right? So repeatedly we'll compute the negative log likelihood. How do we do it? Well, using the trick that I described here. What we'll do is we'll do x times P plus 1 minus x times 1 minus P. So what that does is it just computes all of those likelihoods together, right? So x is a whole tensor. You just do a vectorized version of this essentially. Now you take the log of everything. Now you take the sum of everything. Make sure to use Torch here. So the Torch versions of sum and log, because otherwise things would not work when you do NLL backwards. And in fact, they would not work in other ways. So this would be the negative log likelihood, the thing that we want to minimize. How would we minimize it? We say NLL.backward. So what that does is populate p.data with the gradient of NLL with respect to p. In fact, it's a little bit more complicated than that, because p.data, if it's not 0 initially, then you'll just add the current gradient of NLL with respect to p. Not something that you want to do, so we'll set p.grad to 0 every time after we're done updating p. So we compute the gradient, so let's actually do that. So now NLL is going to be this, some number, and p.grad.data is going to be minus 130. So what does it mean? It means that if you increase p, then NLL will go down by quite a lot. So you increase p by 1 unit, NLL will go down because of the minus by 130. So, okay, that makes sense because p is 0.56, but when NLL is minimized, p should be 0.725. So p should go up and NLL will go down accordingly. Great, and this is the update. So we'll subtract p.grad.data from p.data. So we'll update p.data using this update rule, and it will work, right? Because this is negative, we are subtracting it, so p.data is going to increase. The value of p is going to increase after one iteration. What I'm doing here is I'm just printing out what's going on. So here I'm printing out the value of NLL. I could just say NLL.data, but I convert it to NumPy just because it will display nicer. I also compute p, and I also display p.grad.data, so the gradient of the NLL with respect to p. Finally, I zero out p.grad so that I can start all over again and do another step. So let's run this. And what you see is, yes, you got to p equals to 0.725. Great. So in general, you wouldn't just say for t in range 1000, you would say, well, I'll run things until the parameter stops changing or until the cost stops changing, like maybe until the negative log likelihood stops changing, or until this is 0, or in case there is a danger of overfitting, you'll also see what the performance is on the validation set, and then once that starts increasing because you're overfitting, then you'll stop. Or at least if you see that the performance on the validation set is not improving, so the cost on the validation set is not decreasing for a while, you'll say we'll stop. That's called early stopping. So, okay, so this is how you get the maximum likelihood estimate. Now, let's say that you have a prior. Let's say that you think that p is actually close to 0.5, meaning that the coin is close to fair. But you don't know exactly how close, so you want to trade off basically adjusting p so that it fits the data the best and making sure that p is close to 0.5. How would you do that? So that's what regularization in a way is all about. So we'll do it in this example. So what I'll do is instead of minimizing the NLL, I'll define a cost here. So the cost here is going to be NLL plus lambda, so I predefined my lambda to be 1000, kind of large, times, I'll say p minus 0.5 all squared. And now I'll say cost dot backwards. So now instead of trying to make NLL as small as possible, I'm trying to make cost as small as possible. Except cost is the NLL plus this. So now I'm trying to simultaneously, I want this to be small and I want this to be small. And this is going to be small when p is equal to 0.5. And this is going to be small when p is equal to 0.725. So there's going to be a trade-off and p is going to end up somewhere in between. So let me try this. So p ended up really close to 0.5 just because this lambda is very large. If I decrease it, if I make it like 0.1, then p is pretty much what it was before. Of course, if I make lambda be equal to 0, then this part has no effect at all because it's 0. So this is how we do regularization, if you want to call it that, in this case. Sometimes what you want to do is you just want the parameters to be as close as possible to 0, right? Not to 0.5. So here it's hard to make a case for why you would want that, but let's do it just the same. So instead of adding p minus 0.5 squared, which is going to be small when p is equal to 0.5, you'll say p dot norm all squared. So that's going to be basically p squared in this case. The reason I'm saying p dot norm is that this would work even if p is not just a tensor with one number, but if it's a tensor with lots of numbers, p dot norm would still compute the L2 norm here. Okay, so let's try to do it. So we'll increase lambda to, let's say, 1.0. And what you see is that that was not really enough. Well, now p became smaller, and that was too large. So here we made p really small. So the larger lambda is, the more p gets pulled towards 0, and the more the NLL basically gets ignored because this term is so much larger. Okay, so make sure that you don't do this. So you might sometimes do this if you have justification for that, if you have some kind of prior, although so the prior would also involve figuring out what the lambda should be exactly. Okay.